Welcome back. My name is Norbert Marta. Last time, Attila Birds has spoken about the conversion of solar energy into heat. Now, I will speak about another way how to use solar energy, how we can convert solar energy into electricity. In this chapter, we will learn important definitions. Without this, we can't understand the operation of solar system. We will see the short history of electricity, and finally we will learn the operation of solar panels and see the key features. Let's start our course. Conversion of solar energy into electricity. First, what is electricity? Electricity is all around us, powering technology like our fridges, TVs, lights, and almost all. Is thought to escape it in our modern world. Even when you try to escape electricity, it is still at work through nature, from the lightning in a thunderstorm to the synapses inside our body. But what exactly is electricity? This is a very complicated question, and as you dig deeper and ask more questions, there really is not a definitive answer, only abstract representations of how electricity interacts with our surroundings. Electricity is briefly defined as the flow of electric charge, but there is so much behind that simple statement. Later, I will answer for the main questions. First, we will learn about the history of electricity. In the ancient times, the Egyptians are known to have used the electric Nile catfish to treat headaches and nerve pain. Scinobunus Largus, a physician in the Roman time, is reported to have written that this fish could be used to treat a wide variety of ailments. They were used to numb the feet of good sufferers as well as those suffering from persistent headaches. We have evidence that the ancient culture not only recognized electricity but harnessed it and learned how to generate it. In the primary school, we generated electricity with help of a plexiglass rod and piece of cotton. We rubbed the rod with the cotton and touched the plexiglass to the hair of a student. As a result, the hair rose up. Asian cultures had no plexiglasses. They, they had rod of amber, could be rubbed with cat's fur to attract light objects like feathers. According to a controversial theory, the Parthians, though this territory is in Iraq, may have had knowledge of electroplating based on the 1936 discovery of the Baghdad battery, which resembles a galvanic cell, though it is uncertain whether the artifact was electrical in nature. It was a pot inside the mouth of the jar. A tube of copper was held in place with an asphalt seal, and inside the tube of copper there was an iron rod, also held in place by asphalt. The whole thing could have functioned as a wet cell battery. All the battery needed was the addition of an acid. Numerous acids would have been available at the time, including citrus juice and vinegar, but this is only just a theory. Step by step, we travel to the present times. Electricity would remain little more than an intellectual curiosity for millennia until the first industrial revolution. Benjamin Franklin's electricity experiments showed just how little we knew about electricity in the era of this first industrial revolution. Since Franklin's experiments, our knowledge about electricity has grown tremendously. But what was his experiment? In June 1752, he is reputed to have attached a metal key to the bottom of a damped kite string and flown the kite in a storm-threatened sky. Such action of sparks jumping from the key to the back of his hand showed the connection between lighting and electricity. He was commonly taught during his day that electricity was created by friction, as when a cloth is rubbed against something, but Franklin discovered that electrical charge has held statically in positive and negative quantities in various items, and rather than being created, electricity is only transferred from one item to another. This is what we today call the principle of conservation of electric charge. In addition to discovering the principle of conservation of electric charge, Benjamin Franklin was the first person to use the terms positive and negative when referring the electrical charges. Some other interesting and important things without we can't understand the electricity. I think everybody knows this famous man. The first is Luigi Galvani. He was an Italian physician, physicist, biologist, and philosopher who discovered animal electricity. He is recognized as the pioneer of bioelectromagnetics. Galvani coined the term animal electricity to describe the force that activated the muscles of his specimens. Along with contemporaries, he regarded their activation as being generated by an electrical fluid that is carried to the muscle by nerves. The second one is Alessandro Volta, who was an Italian physicist. He invented the electric battery. Volta's battery consisted of alternating discs of zinc and silver, separated by paper or cross-soaked either in salt water or sodium hydroxide. 6 weeks after Volta's announcement about his battery, two English scientists used this to separate water to hydrogen and oxygen. This was the first electrolysis. How electric current leads to chemical reaction. You know Michael Faraday, who contributed to the study of electromagnetism and electrochemistry. His invention of electromagnetic rotary devices formed the foundation of electric motor technology, and it was largely due his efforts that electricity became practical for use in technology. We had so many great scientists throughout history. It is impossible to recite them all. The last one from his age is Georg Ohm, the German physicist. He mathematically analyzed the electrical circuit which is known as Ohm's law. We have learned about Ohm's law at first in the primary school, but let us see what this was. The amount of steady current through a large number of materials is directly proportional to potential difference or voltage across the materials. Thus, if the voltage in units of volts between two ends of a wire made from one of these materials is tripled, the current amperes also triples. Quotient volts per amperes remains constant. The quotient volt per amperes for a given piece of material is called its resistance, measured in units named ohms. And we arrived to the early 20th century. Earlier, I have mentioned Albert Einstein, who I consider to be the most famous scientist in the world. He won the Nobel Prize in 1921 for his services to theoretical physics and especially for his discovery of the law of photoelectric effect. But what is photoelectric effect and why is it important for the solar cells? As you see on the picture behind the text, if light will shine on a metal, electrons can be ejected from the surface of metal in a phenomenon known as a photoelectric effect. Let me explain. When a photon hits the metal surface, the photon's energy is absorbed by an electron in the metal. If the incident light had a frequency less than a minimum, then no electrons were reacted regardless of the light amplitude. This minimum frequency is also called the threshold frequency. Its value depends on the type of metal. If the frequency of red light is less than the threshold frequency of metal, there is no electrons which are reacted. For frequencies greater than threshold frequency, electrons would be reacted from the metal. The green and blue light causes photoemissions but the blue light has more amplitude, so the electrons are reacted with more kinetic energy. Thanks to this discovery, we can use the solar cell because the solar cells employ the photoelectric effect. In 1959, the first mass-produced silicon-based transistor was invented. Transistors are the key active components in practically all modern electronics, and the silicon is the most important material in the solar cells. As I said earlier, electricity is the flow of electric charge. On the last slide, when I explained the photovoltaic effect, I mentioned the word electron. Do you know what atoms and electrons are? The smallest parts of the life and matter is the atom. At the center of an atom is the nucleus. The nucleus is made up of particles called protons and neutrons. Electrons revolve around the nucleus in shells. The protons and electrons of an atom are attracted to each other, and each carries an electric charge. Protons have a positive charge and electrons have a negative charge. The positive charge of the proton is equal to the negative charge of the electron, making the atom balance with when they have an equal number of protons and electrons. Neutrons carry no electric charge, and their number may vary. The electrons in the shell closest to the nucleus have a strong attraction to the protons. Sometimes the electrons in an atom's outermost shells do not have a strong attraction to the protons and can be pushed out of their orbits, causing them to shift from one atom to another. These shifting electrons are electricity. Let's talk about how we can produce electricity. Earlier, we have learned about what non-renewable and renewable sources are. As we already know, sunlight is a renewable source, and the energy which is generated from it is green energy. But how does electricity work? Electricity travels in closed circuits. It has to have a complete path before electrons can move through it. When you turn on a light by flipping a switch, you close a circuit. Of course, this means that flipping a switch off, you open a circuit. Electricity flows from the electric wire through the light and back into the wire. The same concept applies to your television or your appliances. When you turn them on, you close the circuit for electricity to flow through the wires and power them. Behind the text, you can see a turbine. Why do you need turbine if you make electricity from coal? I will tell you. Coal is milled into a fine powder and it's blown into a combustion chamber or boiler and burned at high temperature. The gases and heat energy produced converts water into steam. The steam passes through the turbine containing thousands of propeller-like blades. At the end of these propellers, a generator sits mounted at one of the turbine shafts. When the generator's coils are rotated in a strong magnetic field, electricity is created. The energy from the nuclear power plant works same, but the heat comes from chain reaction of urine. Now I will share the short story of solar panel. In the early 18th, the solar energy was used for the production of steam. In 1839, French physicist Edmond Becquerel discovered the photovoltaic effect while experimenting with a cell made of metal electrodes in a conducting solution. He noted that the cell produced more electricity when it was exposed to light. Later, in 1873, Wilbur Smith discovered that selenium could function as a photoconductor. Just 3 years later, William Grill Adams and Richard Evan Day applied the photovoltaic principle discovered by Becquerel to selenium. They recorded that it could, in fact, generate electricity when exposed to light. Becquerel's discovery then led to the invention in 1883 by Charles Fritts of the first genuine solar cell, which was formed by coating sheets of selenium with a thin layer of gold. And from his humble beginning would arise the device we know today as a solar panel. Behind the text, you can see the first solar cell. Some interesting fact. Unbelievable that the first solar panel was installed in 1884 in the USA, New York. Its efficiency was 1 or 2%. On the right side of the picture, you can see it. Nowadays, the efficiency is about 20%. We arrived to the middle of the 20th century. Russell Lowell, the American inventor of the Bell Laboratories, patented the world's first silicon solar cell in 1941. Lowell's invention led to the production of the first solar panel in 1954 by the Bell Laboratories. As we earlier have seen, solar panels found their first mainstream use in space satellites. It was too expensive to use on a common way. For most people, the first solar panel in their life was probably embedded in their new calculator. Today, solar panels or complete solar panel systems are used to power a wide variety of applications. On this slide, you can see how a solar system is built up. From the left to the right, I explain the parts of this system. The first one is a solar panel which collects the sunlight. Under it, we can see the combiner box. Its role is to bring the output of several solar strings together. To the right, there is a charge controller. The main role of controller is to protect and automate the charging of the battery. In the middle of the picture, you can see the inverter. The inverter is one of the most important and most complex components of an independent system. The inverter converts direct current to alternating current and also changes the voltage. In other words, it is a power adapter. It can allow a battery-based independent power system to run conventional appliances throughout conventional home wiring. Under that, there is a battery. The battery is a device that stores chemical energy and converts it to electricity. On the right side, you see the breaker panel. Power comes to your home from the solar system and goes to appliances. It controls the power which goes to the appliances. Under the breaker panel, we find the generator. The generator starts automatically when the battery is low. This is not required for a normal solar system. Now we learn what silicon solar cells are and how they are built up. On this picture, you see a cell. Solar cells convert light energy into electrical energy either indirectly by first converting it into heat or through a direct process known as the photovoltaic effect. The most common types of solar cells are based on the photovoltaic effect, which occurs when light falling on a two-layer semiconductor material produces a potential difference, or voltage, between the two layers. The voltage produced in the cell is capable of driving a current through an external electrical circuit that can be utilized to power electrical devices. So basic? Not. But at first, it is enough. An individual photovoltaic cell produces an open circuit voltage of about 0.5 to 0.6 volts at 25 Celsius. This cell voltage remains fairly constant just as long as there is a sufficient irradiance light from dull to bright sunlight. Open circuit voltage means that the PV cell is not connected to any external load and is therefore not producing any current flow. When connected to an external load, such as light, the output voltage of the individual cell drops about 0.46 volts as the electrical current begins to flow, and will remain around this voltage level regardless of the sun's intensity. Today, the most common photovoltaic cells employ several layers of doped silicon, the same semiconductor material used to make computer chips. As you see, there are two types of silicon, N and P type. Now, this time. What do you think? Where does the silicon come from? From the air? No. From the water? No. From the sand? Yeah, it comes from the sand. But what is it? Silicon is a chemical element, a hard, brighter crystalline solid with a blue-gray metallic cluster and semiconductor. Most silicon is used commercially without being separated and often with little processing of the natural minerals. Such use includes industrial construction with clays, silica sand, and stone. In the second part of the 20th century, this is the Silicon Age. Silicon is used in the modern electronic devices, such as in transistors, computers, mobile phones, and etc. As we know, the silicon is used in the solar cells too. Now, let us talk in more detail about how a solar cell works. Today, the most common photovoltaic cells employ several layers of doped silicon, the same semiconductor material used to make computer chips. Their function depends upon the movement of charge carrying entities between successive silicon layers. In pure silicon, when sufficient energy is added, some electrons in the silicon atoms can break free from their bonds in the crystal, leaving behind a hole in an atom's electronic structure. These freed electrons move around randomly through the solid material, searching for another hole with which to combine and release their excess energy. Functioning as free carriers, the electrons are capable of producing an electrical current, although in pure silicon there are so few of them that current levels would be insignificant. However, silicon can be modified by adding specific impurities that will either increase the number of free electrons or the number of holes, because both holes and electrons are mobile within the fixed silicon crystalline lattice. They can combine to neutralize each other under the influence of an electrical potential. Silicon that has been doped in this manner has sufficient photosensitivity to be used in a photovoltaic application. In a typical photovoltaic cell, two layers of doped silicon semiconductor are tightly bonded together. One layer is modified to have excess free electrons, it's an N-type, while the other layer is treated to have an excess of electron holes or vacancies, this is P-type. When the When the two dissimilar semiconductor layers are joined at a common boundary, the free electrons in the N layer cross into the P layer in an attempt to fill the electron holes. The combining of electrons and holes at the p-n junction creates a barrier that makes it increasingly difficult for additional electrons to cross. As the electrical imbalance reaches an equilibrium condition and fixed electric fields result across the boundaries separating the two sides. When the light of an appropriate wavelength strikes the layered cell and is absorbed, electrons are freed to travel randomly. Electrons close to the boundary can be swept across the junction by the fixed field. Because the electrons can easily cross the boundary but cannot return in the other direction, a charge imbalance results between the two semiconductor regions. Electrons being swept into the N layer by the localized effect of the fixed field have a natural tendency to leave the layer in order to correct the charge imbalance. Toward this end, the electrons will follow another path if one is available. By providing an external circuit by which the electrons can return to the other layer, a current flow is produced that will continue as long as light strikes the solar cell. In the construction of a photovoltaic cell, metal contact layers are applied to the outer faces of the two semiconductor layers and provide a path to the external circuit that connects the two layers. The final result is a production of electrical power derived directly from the energy of light. Now you see the structure of solar cells. The blue and red bands are silicon layers, N and P-type layers. These are made from silicon and thick, monocrystalline or polycrystalline. There are many different cell sizes and configurations available. Above you see the glass. The front glass sheet protects the solar cells from the weather and impact from hail or airborne debris. The glass is typically high-strength tempered glass, which is 3 to 4 mm thick and is designed to resist mechanical loads and extreme temperature changes. This type of glass is much safer than standard glass. The next one is a module encapsulant. It is made from ethylene vinyl acetate, which is specially designed polymer, highly transparent. Plastic layers used to encapsulate the cells and hold them in position during manufacture. The lamination either side of the PV cells provides some shock absorption and helps to protect the cells and interconnecting wires from vibration and sudden impact from hailstones and other objects. The yellow one is the backsheet. The backsheet is the rearmost layer of common solar panels which acts as a moisture barrier and final external skin to provide both material protection and electrical insulation. The backsheet material is made of various polymers or plastic. The solar cells out in aluminum frame which plays a critical role by both protecting the edge of the laminate section housing the cells and providing a solid structure to mount the solar panel in position. And how are the solar panels built? On this picture, you can see how we can go from the solar cell to the solar array. Multiple solar cells is in integrated group or oriented in one plane, constitute a solar photovoltaic panel or module. Photovoltaic module often have a sheet of glass on the sun-facing side, allowing light to pass by protecting the semiconductor wafers. Solar cells are usually connected in series creating additive voltage. Connecting cells in parallel yields a higher current. And some questions. We use EC and DC, but a lot of people don't know what is the difference between them. Why do we use EC at the electrical grid? I have talked about the inverter. Do you remember? Why do we need it? The answer is that alternating current, this is the EC, is an electric current which periodically reverses direction and changes its magnitude continuously with time in contrast to direct current DC, which flows only in one direction. Alternating current is the form in which electric power is delivered to the businesses and residences, and it is the form of electrical energy that consumers typically use when they plug household appliances. A common source of DC power is, for example, a battery cell in your flashlight. Alternating current systems can use transformers to change voltage from low to high level and back, allowing generation and consumption at low voltage when transmission, possibly over great distances at high voltage, with saving in the cost of conductors and energy losses. As we know, the inverter converts DC to EC and also changes the voltage. AC is the standard form of electricity for anything that plugs in to utility power. And now we move on to the solar cell's efficiency. This refers to the portion of energy in the form of sunlight that can be converted via photovoltaic into electricity by the solar cell. Energy conversion efficiency is measured by dividing the electrical output by the incident light power. The efficiency of the solar cells used in a photovoltaic system in a combination with latitude and climate determines the annual energy output of the system. For example, a solar panel can produce more energy when the sun is high in the sky and will produce less in cloudy conditions or when the sun is low in the sky. The sun is lower in the sky in the winter. The efficiency depends on type of solar cells as well. Next time you will see the different types of solar cells. On this graph, you see the efficiency of the different types of solar panels. The blue lines are the common solar panels which are used on the rooftops and fields nowadays. The purple lines are multi-junction solar cells. Solar cell efficiencies vary from 6% for amorphous silicon-based solar cell to 44% with multiple junction production cell and 44.4% with multiple dies assembled into a hybrid package. The multicrystalline solar panel's efficiency is about 90%. But how can we increase of efficiency? Some factors affect the efficiency of energy conversion. Let's see this. Choosing optimum transparent conductor. The illuminated side of the illuminated side of some types of solar cells, thin films, have a transparent conducting film to allow light to enter into the active material and to collect generated charge carriers. Typically, films with high transmittance and high electrical conductance, such as indium tin oxide, conducting polymers, or conducting nanowire networks are used for the purpose. There is a trade-off between high transmittance and electrical conductance, thus optimum density of conducting nanowires on the conducting network structure should be chosen for high efficiency. The next one, promoting high scattering in the visible spectrum, lining the light reviewing surface of the cell with nano-sized metallic studs can substantially increase the cell's efficiency. Light reflects off these studs at an oblique angle to the cell, increasing the length of the light passed through that cell. This increases the number of photons absorbed by the cell and the amount of current generated. Radiative cooling. An increase in a solar cell temperature of approximately 1 Celsius causes an efficiency decrease of about 0.45%. To prevent this, a transparent silica crystal layer can be applied to solar panels. The silica layer acts as a thermal blackbody which emits heat as infrared radiation into space, cooling the cell up to 13 degrees. Anti-reflective coating and texture. Anti-reflective coating could result in more destructive interference of incident light waves from the sun. Therefore, all sunlight would be transmitted into the photovoltaic. Rare surface passivation. The, the chemical deposition of rare surface dielectric passivation layer stack that is also made of a thin silica or aluminum oxide film topped with a silicon nitride film helps to improve efficiency in silicon solar cells. Earlier, the back surface was only aluminum. On this graph, we see the price history of solar cells in US dollar per watt. Over a decade ago, the cost of a solar panel installation was $8.50 per watt, and now less than half dollar per watt. The difference is huge. This is a big industry. The top 10 manufacturers are Chinese, as the bulk of the global solar panels are manufactured there. But the EU also plays a big part in it. Since 2013, China has been the world's leading installer of solar photovoltaics. Next time, Attila Burrows will show you the different types of solar panels. Thank you for your attention. I hope you have enjoyed it. Bye.